Before we begin, I have one simple question. Could time travel ever work? The truth is that both myth and science point us toward fascinating answers. I'm Gabrielle Burchak, your host. I have a background in math, science, and journalism, and today we question, is time travel only fantasy, or is it in some strange and precise way actually possible? Stay tuned, you'll soon find out. Do you want to time travel with me today? You can by subscribing to the ad-free feed on Supercast. You can jump ahead in time and listen to next week's episode right now, today. No waiting, no paradoxes, just instant access. So, what is Supercast? Well, it is a podcaster's platform that allows you to sign up for ad-free podcasts on any of your favorite podcast players. I have 3 tiers that offer some fantastic benefits to your membership. You can get ad-free podcasts a week in advance, and other tiers include discounts on merchandise, research notes, and a mention on the podcast. So visit us at mathsciencehistory.supercast.com. And the link will also be in our show notes. It will also be on our website at mathsciencehistory.com. It's everywhere. So what's it going to be? Are you going to stay here in the present or take a leap into the future with me? Imagine stepping into a machine, an elaborate chamber of brass, gears, and humming coils. You sit down, pull a lever, and suddenly the world outside your window blurs. The clock on the wall no longer ticks in neat, familiar seconds. Instead, time itself bends and stretches like taffy. Days whirl past in moments. Centuries collapse into a single breath. And before you can even blink, you are no longer where or when you started. This vision has haunted and thrilled humanity for centuries. Time travel is more than a trope in science fiction. It is a longing, a human ache to rewrite tragedy, to see our ancestors, or to leap forward and glimpse at what awaits us. From myths of enchanted slumber to modern physics equations scribbled on chalkboards, the dream has never left us. The truth is that both myth and science point us toward fascinating answers. Ancient storytellers gave us tales of travelers who stepped outside of time and returned to find their worlds forever changed. Later, writers like H.G. Wells transformed those dreams into concrete visions of machines that could conquer the clock. Albert Einstein shook the scientific world with equations, showing that time is not absolute. It bends, it stretches, and under the right conditions, it can even loop back on itself, as shown by physicist Dr. Ronald Mallett. Tangible proof. So today, we're going to take a journey of our own. We will explore the myths and the literature that gave birth to the idea of time travel. We will examine the real-life scientists and dreamers who tried to build machines and who did build machines to make it happen. And we will look at the profound theories from Einstein's relativity to modern wormhole physics that suggest time travel isn't just possible in fiction, but within the very laws of our universe. Could time travel ever work? That's a great question. Let's find out. Long before laboratories, equations, and particle colliders, humanity imagined stepping outside of time. Ancient myths across cultures tell stories that, in hindsight, feel like prototypes for modern science fiction. In Hindu mythology, the Mahabharata tells of King Kakudni, who traveled to the realm of the creator god Brahma with his daughter Revati to find her a suitable husband. There, he and Revati waited while listening to a musical performance. When they approached Brahma, Brahma burst into laughter. He told the king that while he and Revati were waiting, thousands of years had gone by. All the potential husbands on King Kakudni's list were long dead. In Japan, the tale of Urashima Taro describes a fisherman who rescues a turtle and is rewarded with a journey under the sea. He stays only what feels like a few days, but when he comes home, centuries have slipped by and his entire life is unrecognizable. These stories capture the essence of what physicists would one day call time dilation, where time does not pass equally for everyone. By the 18th and 19th centuries, Western literature had begun to formalize the theme. Washington Irving's Rip Van Winkle, written in 1819, gave American audiences a man who fell asleep in the Catskill Mountains and awoke 20 years later, bewildered by the revolutionized world around him. Charles Dickens, in his book A Christmas Carol, written in 1843, used the device of spectral journeys through past, present, and future to force Ebenezer Scrooge into redemption. These tales were not scientific, but they captured something profound. Time could be manipulated. It could be jumped across, even if only in imagination. But the true turning point came in 1895 when H.G. Wells published The Time Machine. Wells didn't just tell a story, he invented the language we use today. He coined the very phrase time machine, and more importantly, he treated time as a dimension, just like height, width, and depth. His time traveler doesn't rely on magic or divine intervention. Instead, he uses a machine built with logic and engineering to travel through centuries. Wells turned time travel from a dream into a concept that could be visualized, debated, and perhaps someday, one day, tested. Only a decade later, in 1905, Albert Einstein published his theory of special relativity. In it, time was no longer absolute. It was elastic depending on how fast you moved. The faster you travel, the slower time passes for you relative to others. Suddenly, science was speaking the same language Wells had imagined. Einstein's later work on general relativity in 1915 showed that gravity itself could bend time, opening the door to the possibility of closed time loops and wormholes. The leap from Wells' fictional time traveler to Einstein's mathematical spacetime was monumental. One showed us the dream in narrative form. The other gave us equations proving that the dream might, under certain conditions, be reality. Fiction and physics were no longer separate worlds. They were now part of the same conversation. And this is where our story pivots. From here on, time travel would not only belong to storytellers, but also to scientists who wonder, if time is malleable, then how far can we push it? Can a machine like Wells ever be more than a metaphor? So if H.G. Wells gave us the dream of a time machine, Albert Einstein gave us the blueprint, or at least the equations that hint at one. Einstein's work at the beginning of the 20th century changed everything about how scientists thought of time. Up to that point, time was treated as a constant, ticking along in the same rhythm for everyone, everywhere. But Einstein showed us that time doesn't march. It stretches, it bends, and it even loops under the right circumstances. In 1905, Einstein introduced his theory of special relativity. Its key idea was revolutionary. The faster you move, the slower time passes for you compared to someone standing still. This isn't science fiction. It has been measured. To make sense of this, physicists often describe the twin paradox. You've probably heard of it. Imagine two twins. One stays on Earth, the other boards a spaceship traveling close to the speed of light. To the seafaring twin, the journey might feel like a few years. But when they return home, they'll find their sibling has aged decades more. In other words, traveling near the speed of light lets you move into the future faster than those who stay behind. That is time travel, at least one way. You can leap forward in time simply by moving very, very fast. The catch? Achieving those speeds takes astronomical amounts of energy, but the principle is sound. 10 years later, Einstein expanded his ideas with the theory of general relativity. Yeah, I know it's confusing. My husband always asks me, which comes first, general relativity or special relativity? It makes no sense. And I always say it's special relativity. Anyhow, this theory doesn't just describe how objects move. It redefines gravity itself. Instead of an invisible force pulling objects together, gravity becomes the curvature of space-time. Imagine space-time as a stretched rubber sheet. A bowling ball is placed on the sheet, and the sheet sinks, bending the surface. Smaller marbles roll toward the ball, not because the bowling ball is pulling them, but because the sheet is curved. Now, replace the sheet with space-time and the bowling ball with the planet or a star. Space-time curves around mass, and objects, including light and time itself, must follow those curves. That's why light bends near stars and why time slows down near strong gravitational fields. General relativity also introduced a wild possibility: closed, time-like curves. These are paths through space-time that loop back on themselves. If you followed one, you could, in theory, return to your own past. In everyday life, we walk forward in space but never circle back to where we started in time. Closed, time-like curves would change that, offering a kind of built-in cosmic time machine. Physicists like Kurt Gödel and Frank Tipler explored such solutions mathematically. Gödel, spelled Godel, pronounced Gödel. Gödel, for example, proposed a model of the universe that rotated, creating a structure where time could loop back endlessly. It was strange, impractical, and probably not our universe, but it showed that general relativity did not forbid time travel. The first tangible test of Einstein's ideas about time came in 1971 with the Heffele-Keating experiment. Two physicists, Joseph Heffele and Richard Keating, carried 4 cesium beam atomic clocks onto a plane. They flew eastward around the Earth and then westward and compared the airborne clocks with identical clocks left on the ground at the United States Naval Observatory. The results? The airborne clocks showed measurable time differences in elapsed time compared to those on Earth. Flying eastward with the planet's rotation, the clocks lost time. Flying westward against rotation, they gained time. The differences were tiny, mere billionths of a second, but exactly what Einstein's theories predicted. Was this the first true experiment in time travel? In a sense, yes. The airplanes didn't vanish into the past or visit the year 3000, but they demonstrated that time moves differently depending on speed and gravity. Time travel, even if only in fractions of a second, had been observed and measured. Now, if airplanes can shift clocks by fractions of a second, imagine what massive cosmic objects can do. Near a black hole, where gravity is intense, time slows dramatically compared to regions further away. Physicists call this gravitational time dilation. If you orbited safely near the edge of a black hole, hours for you might equal years for someone far away. In fact, the movie Interstellar drew directly from real physics when it showed astronauts experiencing a few hours near a black hole, only to return to find that decades had passed for their colleagues. The science behind that scene was advised by Kip Thorne, one of the foremost physicists of our time. This effect is one way toward the future. You could never use a black hole to go back and stop yourself from falling in. But you could, in theory, use gravity to leap ahead into the future far faster than those who remain behind. Black holes may slow time, but wormholes, called Einstein-Rosen bridges, promise shortcuts. Imagine space-time not as a flat sheet, but as a folded piece of paper. If you draw 2 dots on opposite sides of the paper, the shortest path is a straight line. But when you fold the paper so the dots touch, suddenly they are connected by a single point. That is the idea of a wormhole, a tunnel connecting 2 regions of space-time. Kip Thorne and his colleagues explored whether wormholes could, in theory, allow not just travel between distant parts of space, but also different points in time. The mathematics suggest that if one mouth of a wormhole experiences time differently from the other, say by placing it near a black hole, then stepping through could deliver you into the past relative to where you started. The obstacles? Well, they are immense. Wormholes may collapse instantly without exotic matter to hold them open. Exotic matter is a hypothetical material with negative energy density, something we have no evidence for. Still, wormholes remain one of the most popular theoretical blueprints for time travel because the equations allow them. What Einstein revealed and what experiments in cosmic objects continue to suggest is that time is not fixed. It is flexible, relative, and deeply tied to the fabric of the universe. Time travel to the future has already been proven in airplanes, satellites, and near-massive objects. The harder challenge, the Holy Grail, is traveling to the past. And that challenge was irresistible. It wasn't enough for scientists to sketch wormholes on chalkboards or for theorists to imagine closed, time-like curves. Some inventors, physicists, and even dreamers outside the mainstream began asking, can we build a time machine to make it happen? We'll be right back after a quick word from my advertisers. So far we've seen how relativity bends time, how black holes slow it down, and how wormholes might connect one moment to another. But the deeper the physicists push into the math, the stranger the possibilities become. Some proposals offer real, if wildly impractical ways of bending time into loops. Others run headfirst into paradoxes, those logical dead ends that make your brain itch. Earlier, I mentioned Kurt Gödel. He was a mathematician, and in 1949, he became famous for his incompleteness theorems, and he applied this genius to Einstein's equations. He discovered a solution describing a universe that rotated on a cosmic scale. In this spinning cosmos, time itself would curve into closed loops, meaning you could, in theory, circle back to your own past. This sounds truly amazing, right? Okay, here's the catch. Gödel's universe didn't match reality. Our universe isn't rotating that way. Still, Gödel proved that Einstein's equations don't forbid time loops. Gödel's physics points out that maybe the universe doesn't mind a little backward stroll. Einstein admired Gödel's brilliance, but found the idea disturbing, believing that backward time travel could be impossible even though he had no formal proof. He could dismiss Gödel's model on the grounds that our universe clearly wasn't rotating that way, but his discomfort ran deeper. Philosophically, he valued causality, the simple idea that causes precede effects, and practically, he likely suspected that additional, still unknown laws, perhaps from quantum physics, would close off Gödel's time loops. For these reasons, Einstein never validated Gödel's theory. He respected the mathematics, but treated it as a curiosity rather than a description of reality. Privately, though, he seemed troubled that his own equations permitted something he found absurd. A tension that later inspired Stephen Hawking to suggest his chronology protection conjecture as a way to close the very loopholes Gödel had exposed. And so before I get into Hawking, speaking of chronology, let me tell you first about physicist Frank Tipler. Frank J. Tipler, born in 1947, is an American mathematical physicist who studied under John Wheeler. And this is the same Wheeler who coined the term black hole. I did a podcast on that one too. In the 1970s, Tipler was working on solutions to Einstein's general relativity equations, asking what kinds of space-time geometries might allow for unusual effects, including time travel. Decades after Kurt Gödel spun up his rotating universe, another physicist decided to test the limits of Einstein's equations. So in 1974, Tipler proposed what became known as the Tipler cylinder, a kind of a blueprint for relativistic time machine. So picture it. An unimaginably massive cylinder, infinitely long, spinning at nearly the speed of light. The faster it spins, the more it drags space-time around with it. A phenomenon we now call frame dragging, which satellites have actually observed around Earth. It exists. Now crank that effect up on a cosmic scale. Near Tipler's cylinder, space-time itself would twist so severely that time would bend into loops called closed time-like curves. Fly a spaceship close enough, Tipler argued, and you could trace a path through space-time that carried you into your own past. It's elegant on paper, but here's a catch, or several catches. First, Tipler's solution requires the cylinder to be infinite in length, not very practical. Finite versions have been studied, but the math shows that once you cut the cylinder down to size, the time loops disappear. Second, the amount of mass required is absurd, comparable to compressing an entire star into a structure that spins at nearly light speed. And finally, later physicists, including Hawking, argued that even if you could build such a device, quantum effects would likely make it collapse before any time traveler could take a ride. So, does Tipler's idea hold validity? Mathematically, yes. It's a rigorous solution to Einstein's field equations. But physically, no. At least not in any way we could hope to engineer. Most scientists view it as a thought experiment, a way to test the outer boundaries of relativity rather than a literal blueprint. Still, Tipler's cylinder remains important. Like Gödel's rotating universe, it demonstrated that Einstein's equations don't forbid time travel outright. They leave the door cracked open, if only by a sliver. Tipler himself later ventured into controversial territory, blending cosmology with theology in his omega point theory. But his cylinder endures as a reminder that sometimes even impossible machines matter. They push the conversation forward, daring us to imagine what relativity really allows. As with so many attempts at time travel, the Tipler cylinder wasn't a failure. It was a proof of possibility written in equations. By the late 20th century, physicists had already produced a series of strange solutions to Einstein's equations: Gödel's rotating universe, Tipler's infinite cylinder, and theoretical wormholes that all suggested time loops might be possible. The math was there, and it was unsettling. If relativity allowed these so-called closed time-like curves, what was to stop someone from jumping into the past and undoing history? So let's fast forward to Stephen Hawking. Fast forward, pun intended. Stephen Hawking decided to confront that question directly. In 1991, he introduced what he called the chronology protection conjecture. His idea was straightforward but profound. While the equations of relativity might allow time travel in principle, the laws of physics as a whole conspire to prevent it in practice. The very act of trying to create a time machine, he argued, would cause the time machine to destroy itself to prevent any events happening that would alter history. The grandfather paradox is one of the most famous logical problems in time travel theory. It questions the consistency of time travel to the past and altering events that would prevent the traveler's own existence. The paradox goes as follows. If a person were to travel back and kill their grandfather before he had children, then the time traveler would never have been born and therefore could not have traveled back to commit the act in the first place. This creates a causal contradiction because an event, the time traveler's existence, both occurs and does not occur. Physicists and philosophers use the paradox to illustrate the potential incompatibility between classical causality and hypothetical backward time travel. In theoretical physics, solutions to the paradox include the Novikov self-consistency principle, which asserts that the laws of physics prevent paradoxical events from happening. Then there is the many worlds interpretation of quantum mechanics, which suggests that traveling to the past creates a new branching timeline, leaving the original history intact. The grandfather paradox remains a cornerstone in debates about whether time travel to the past can be logically or physically possible within the framework of relativity and quantum theory. Then there is the bootstrap paradox. It's also called the causal loop. So imagine you go back in time and hand Shakespeare a copy of Hamlet. He publishes it under his own name. Centuries later, you study Hamlet in school, then bring that same copy back to Shakespeare. Here's the question: who actually wrote Hamlet? The play exists, but it has no origin. It's a Mobius strip of causation. These paradoxes can sound like riddles or jokes, but they pose serious challenges to physics. If time travel to the past were possible, would logic itself break? Another escape hatch is the multiverse idea. According to this view, traveling back in time creates a branch in the timeline. So instead of erasing your own existence, you spin off an alternate universe where events play out differently. You would still exist in your original timeline, but the new one would continue without you. Science fiction fans will recognize this from countless movies where characters hop between branching realities. And so here is the fun part. Paradoxes are less about breaking physics and more about stretching our minds. They are cosmic riddles, forcing us to ask what cause and effect really mean. And paradoxes do something else. They remind us that time travel isn't just about building machines. It's about philosophy, logic, and the limits of what we can even imagine. Now, some people are not satisfied with theory or imagination. They want to build a time machine. Dr. Ronald Mallett. He's a theoretical physicist with the University of Connecticut, and he was inspired by personal tragedy. This one really gets me because I am my father's daughter, without a doubt. His father died when he was 10 years old. That tragic event inspired him to pursue a career in physics at the University of Connecticut, where he became known for his research on Einstein's theories of relativity, black holes, and his pioneering work toward building a theoretical time machine. Dr. Mallett is Professor Emeritus in the University of Connecticut's Physics Department. His work is notable, and he has received several awards for his theories and work, including the Ford Foundation Senior Postdoctoral Fellowship in 1982, an honorable mention for the Gravity Research Foundation Essay Award in 2001, an honorary member of the Connecticut Academy of Arts and Sciences in 2005, an Outstanding Alumni Award from the Pennsylvania State University at Altoona in 2006, and an Alumni Fellow Award from Pennsylvania State University. Mallett's tangible design is based on Albert Einstein's gravitational field equations. He describes this in his book called Time Traveler, where he shows that by applying the standard approximation for a weak gravitational field to Einstein's equations, he was able to reduce the number of terms in the equations. He then calculated the gravitational field of the ring laser that he was working with in this design. After weeks of intensive work, he found that his ring laser had actually produced a gravitational field that was similar to a vortex. This vortex could produce minute effects of frame dragging. This evidence of frame dragging presents possible closed time-like loops. These closed time-like loops? Well, this is time travel. If you want to read more about this, he describes it in his memoir, Time Traveler, a scientist's personal mission to make time travel a reality. It was published in 2006, but it's still available. I finished reading the whole thing about a month ago, and it is so good. And I have exciting news. If you are interested in hearing more about Dr. Mallett's discovery, tune in next Tuesday at Math Science History to hear my interview with Dr. Mallett and listen to his theories and how he obtained tangible evidence of time travel. Again, that's next Tuesday at Math Science History. Stay tuned. So, where does this all leave us? Are we any closer to traveling through time than when H.G. Wells first put pen to paper? The answer is closer, but not quite there. Science thrives on iteration, like Dr. Ronald Mallett's laser loop. These efforts act like stepping stones. They narrow the possibilities, clarify what won't work, and sometimes open unexpected new doors. Mallett's critics argue his design won't produce usable time travel, but his work highlights a crucial truth. Attempts at time travel are experiments that work in another direction. They show us where physics bends and where human imagination presses hardest against the unknown. We now know that time travel into the future is not only possible, but already demonstrated through relativity, atomic clocks, and GPS satellites that must correct for time dilation every day. Travel to the past remains the thorny problem. It's tangled in paradoxes and practical barriers. Wormholes remain mathematically possible, but unproven. Exotic matter needed to stabilize them hasn't been found. Still, Einstein's equations haven't closed the door. They leave cracks, little mathematical whispers that hint at the possibility. As Stephen Hawking put it, the best evidence we have that time travel is not possible is that we have not been invaded by hordes of tourists from the future. I love that. But that doesn't mean the book is closed. What matters isn't whether a machine has been built yet. What matters is the persistence, like Dr. Mallett shows, the willingness to try, fail, and try again. Every failure sharpens our theories and teaches us more about the universe. And in that sense, the search for time travel is already a success. It inspires new generations of scientists to push limits, not only in physics, but in human imagination. If time travel is ever achieved, it will be because people like Dr. Ronald Mallett refused to give up despite the challenges and the critics. In science, as in life, failure isn't the end. It's the path. So with that being said, please tune in next week for this special interview with Dr. Mallett. Thank you for listening to Math Science History. And until next time, carpe diem. Thank you for listening to Math Science History. If you enjoyed today's episode, please leave a rating and a review, because those ratings and reviews really help the podcast. If you would like to listen to Math Science History without the ads on your podcast player, visit us at mathsciencehistory.supercast.com. There, you can sign up for a tier, which will give you early release podcasts, research notes, bonus material, and discounts on our merchandise. Also, you can find the transcripts at mathsciencehistory.com under the link called Transcriptorium. And while you're there, remember to click on that coffee button and make a donation, because every single dollar that you donate supports our production costs and keeps our educational website free. And until next time, carpe diem.